Hi guys, so in this video we're going to go over nuclear radius. We're going to look at how did they use this experiment, and hopefully you're thinking this is the alpha scattering experiment by Rutherford, and this one is our electron diffraction experiment. And these two experiments helped us probe the size of that nucleus. Okay, so for the first one here, it says that we have an alpha particle with 4 mega electron volts of energy, and hopefully you're remembering that 4 mega electron volts is 4 times 10 to the power 6 electron volts. And to get that into joules, we just multiply by 1.6 times 10 to the negative 19. So that's the energy that that alpha particle has. And we know that alpha particle has loads of energy, loads of kinetic energy because it's moving. And what's going to happen is that alpha particle gets fired towards that proton. And what's going to happen is kinetic energy slows down, it slows down, slows down. And the reason it slows down is because alpha particles are positively charged. Because you need to remember that an alpha particle is a helium nucleus, right, 4-2. Because it's just the nucleus, what that tells us is we have 2 protons and 4 take away 2, which gives us 2 neutrons inside that nucleus. So because I have 2 protons, or 2 positive protons, that's why it's got a relative charge of +2. So what we're doing is taking this alpha particle and we're firing it, say something like gold, a gold nucleus. It's really large, it's got 79 protons. So these 2 positive charge things, they want to repel each other. Okay? So there'll be some point when the energy due to that repulsion is going to be equal to the kinetic energy it has. So again, that's why we have to fire it with loads of kinetic energy, because we're trying to go against that repulsive force. So we know from our electric fields topic, around any positive point charge, we have those electric potential lines. So we're trying to find out which electric potential line is the point when the elastic potential energy from repulsion is equal to the kinetic energy. So to find the potential lines, we know we do 1 over 4 pi times epsilon naught Q over R. So Q is a charge here, 79 protons, and R is this distance away. So distance away here is going to be my R. So we know there'll be some potential line, some region around that positive charged nucleus where the energy to put that alpha particle at that point in space is going to take up or equal to all its kinetic energy. Because we know in our way right potential is equal to the work done per unit charge to take a unit charge from infinity and place it at a point in that field. So that's just needing, if you want to recap that, go back to your electric fields. So to figure out what the work done is, we do our potential times by our charge. So to find what the work done is, I take my potential, that's my potential line here, times by the charge I'm putting that point. I'm putting this alpha particle in that point. To see what that work done then is, we do our potential, which was our 1 over 4 pi epsilon naught charge over R, multiplied by the charge we're putting at that point. And the charge we're putting at that point is our alpha particle. So again, that work done is going to be our kinetic energy. We're going to say that all of that kinetic energy is being transferred into that potential energy. So what we're saying then is whatever our kinetic energy was, which is our 4 times 10 to the power 6, because it was mega electron volts, times 1.6 times 10 to the negative 19, to put it into joules, is equal to 1 over 4 pi epsilon naught. The charge of the nucleus we're firing at was 79 protons, or a relative charge of plus 79. We know that actually means 79 times 1.6 times 10 to the negative 19, because it's not actually got a charge of 79. And we're firing our alpha particle at it, which is a charge of 2. So again, we're firing again 2 times 1.6 times 10 to the negative 19. So we've got 2 of those charges. And then we divide by R. So R tells us there, that's going to be what we think the radius of this atom is. So clearly what we're getting here is that value of R. So we're thinking the atom is actually this large. We're not getting the actual radius of the atom. You can see the actual radius of the atom is much smaller. So what we're doing here is we get the closest distance of approach, because the alpha particle can't actually get to the nucleus because, again, of that electrostatic force of repulsion. We can just get close enough to get an approximation for this nuclear size. So then what we did was came along thinking, how can we do this better? And we did this better by our electron diffraction experiment. So we know from our waves topic that electrons can be both particles and waves. Okay, it's called wave-particle duality. And just go back to that topic if you want to revise that. But we know when electrons hits this gold. So let's say we've got a sheet of gold. And we know that sheet of gold, we know solids are made of atoms, and know between those atoms are going to be those tiny little gaps. This is my lattice. Between those little gaps, that's what the electron diffracts between. So you can imagine those little gaps between the atoms. And those little gaps is what the electron diffracts between. And then we're going to get our waves, and we know when we get waves that are going to superpose. We get a diffraction pattern on our screen of our central maximum and then our alternating bright and dark fringes. When they did the electron fraction, what they did was they wanted to find the angle to the first minimum. So again, there's my central maximum, there's my first minimum. So they found out what this angle was here, theta, to that first minimum. And sine of that angle to the first minimum, they found was equal to 0.61 times whatever wavelength of electrons you're using divided by the radius. And again, remember, to find out what the wavelength of the electrons is, we know that we can do the wavelengths, or the de Broglie wavelength is equal to Planck's constant divided by their momentum. Remember, their momentum there is just whatever the mass of an electron is times whatever speed they're moving at. So that's how we can find out what the wavelength of these electrons is. We just do Planck's constant, which is on your data sheet, divided by the mass of an electron times whatever speed that electron is going at to get its wavelength. And that's then we can find out what the size of that nuclear radius is. Okay. The reason why we use this electron diffraction experiment is better. So again, this experiment is better. The reason why it is better is, again, because we're not getting an approximation. Remember, this one is only giving us approximation. So it's better because in the alpha scattering experiment, the alpha particles that are positively charged, so I'm just going to write that quickly for positively charged, they are repelled by the positive nucleus. So we only get a distance or get an approximation of closest approach. But the electrons are not repelled, right? Because they have got an opposite charge. They're not repelled by that positive, they're not repelled by that positive charge nucleus. Another reason is we use leptons because electrons, like I just said there, they're leptons. Another good reason to use them is because they're leptons, they have no interaction with strong nuclear force, but an alpha particle would. Other reasons is they're much smaller, so we're going to have less recoil from that nucleus, and also because they're much smaller, they get much closer together. So lots of reasons why it's better, but the main ones I would learn is that it's better again because the alpha particles are positively charged. They're going to get repelled by that positive charged nucleus. So when we get an approximation, a distance of closest approach, we don't actually get that nuclear size, whereas our electrons are not repelled because they've got opposite charge. And the other point I was right, because it's always a 2-mark question, is that electrons are leptons, so they have no interaction with a strong nuclear force. When we did this, we then also got this equation. So this equation here tells us that the radius of any nucleus is equal to some constant times by A, that's their mass number to the power of a third. And the reason that people always get this equation wrong, we're trying to find out what the radius is, they always have a problem with this mass number. So for example, let's say we're looking at lithium 7,3. The A number, the one we use for the mass number, is the 7 there. So it's going to be 7 to the power of a third. A lot of people try to use that bottom number, but remember A stands for your atomic mass number. Then we can use that to find out what the radius is.